Okay, guys. So let's do number 5 on chapter 15 in equilibrium. Okay, so we're given a mixture of CO2, H2, and H2O, and they have some moles amounts for each of them, and they're placed in a 1 liter flask. Okay, and they're allowed to come to equilibrium, as shown below. At equilibrium, one of our concentrations of CO2 is given to us by some value. What are the equilibrium concentrations of H2, CO, and H2O? Okay, so we're first part A. We're going to do part A and B in this problem. And the first one is asking us to solve for the equilibrium concentrations of H2, CO, and H2O. So notice that any time that you're given this is a mixture is placed in that. So these are all these are all here. These are initial conditions, right? So the idea there is that these are our initial values for our reactants and products, and then we are going to some change is going to occur on their way to reaching equilibrium, right? And this would be our final concentrations. Here are EQ concentration, right? So there's something that happened between the initial conditions to the equilibrium conditions. So now let's try to organize our thoughts to get to that, right? As mentioned in a previous video, the way that we do that is by writing an ICE table, right? The initial leading all the way to the equilibrium, right? So let's construct that, and that will allow us to solve for our equilibrium concentrations. Okay, so let's do that. So then I'm going to write out the equation again. It is a gas plus H2 gas plus H2O. So notice these are all gases, so they'll all be included in our values for Kc and Kp. Okay, so we have this, and then let's just construct our ICE table. ICEQ, right? Okay, so our initial concentration of CO2 is 0.1 mole. It's worth mentioning that I'm going to put something in here, and then I'm going to erase right after. All values are concentrations. Not moles. Okay, so every value that we put in this chart, it has to be a concentration. It can't be moles. So the way that we do that is we divide the moles of what we have by the total value of the volume of the volume of the experiment in this case. So it just so happens that in this case that our volume that this is occurring in is a liter flask. So that means, remember, molarity is equal to moles per liter. So really I'm going to divide all of my values, all my mole values, 0.1, 0.05, 0.1, dividing that by 1. So essentially all of the mole values will be turned into molarity. And this means that the numbers aren't going to change. But you need to be super conscientious of the fact that if there is some number, like let's say our flask was 5 liters, you would have to divide all of the mole values by 5. Okay? So make sure you're aware of that, okay? I'm going to delete this. Moving forward, with every video from now on, I will accommodate for the volume, and I will do that quickly, okay? So I'm not going to be always reminding you guys. I want you guys to make sure you're very conscious of that, okay? So make note, okay? So our initial concentration of CO2 is 0.1 molar. H2 is, so we have that. 0.05 of H2, 0.05 molar, and we have 0.1 mole of H2O. 0.1 molar. Okay. It appears as though we have no CO to begin with. So then I'm going to say my initial value is 0. That's just because they didn't give us a value. Okay. So then at equilibrium, our concentration of CO is 0.0954. 0.954, right? So that means then some change occurred, right? from 0.1 to 0.094, and we need to solve by how much it changed. So let's just subtract 0.1 minus 0.094. And if you do that, you find the value, it changed by a value of negative 0.0046. Okay, so we had initially 0.1 molar, and the concentration changed by a factor of 0.046. Alrighty? So that means then that the good thing is that since we've constructed ice tables before, since we know the change of one reactant, we can solve for the change of everything else in the reaction, right? So now we can solve for H2, CO, and H2O, the changes. So that means our H2, notice that it's a 1-to-1 ratio. So that means it's going to be negative 0.0046, right? Let's see, just double checking it's balanced. Yeah, cool, it's balanced. Make sure that this equation is balanced. We have, otherwise this whole process is for nothing if it's not balanced. Yeah, we appear to be balanced right now. Okay, cool. So it's negative 0.046, negative 0.046. That's because it's a 1-to-1 ratio, so the rate of loss of CO2 and H2 is equivalent. And that means it's also a 1-to-1 ratio for CO and H2O. So it's going to be plus 0.0046 and plus 0.0046 for H2O. Okay, so now we can solve for the equilibrium concentrations of all of these. Remember, this is going to be molarity for all of them. So 0.05 plus 0.0046. If you solve for that, you get 0.0546 molar, right? That looks horrible. I'm just going to erase it. And then this will just be 0 plus that, so 0.0046 molar. And 0.1 plus that, so it's 0.1 plus 0.0046. 0.1046. Okay. So, through this problem, we have solved for the equilibrium concentration. So all of these are the values that we want, right? So then, the equilibrium concentration of so these are essentially what we need essentially for the CO2 and so forth. Okay, and that solves part A. All right. So just remember that whenever you are constructing an ice table, the last row in the ice table corresponds to the equilibrium concentrations of the reaction. It appears that they just wanted the concentrations of H2, CO, and H2O. So that means I really only care about this one, and H2. Okay? So those are the three ones that they actually want in this problem. It appears they don't want CO2. Oh, that's because they gave it to us. Yeah, that's why. So then actually it doesn't matter that we circle it. Yep, that was a given, so then we know everything now. Okay, so we have part A out of the way. We know our equilibrium concentrations. So now we need to calculate Kp and Kc for this reaction. So let's do that. Let's do Kc first. We know that Kc, you should be perfectly comfortable with this now. This idea is that the Kc is the products over the reactants raised to their coefficients. So H2O, CO, H2, and CO2. And all we got to do is plug in the equilibrium concentrations to solve for that. So we need to plug in the values of the last row of the ice table. So H2O has a value of I don't need to put it in brackets anymore, 0.1046, 0.0046 all over 0.0546 and 0.0945, 954 rather. And that will give us our value for our Kc. 0.1046. Okay, so then I have my number, 0.0923. That is equal to my Kc value. It appears we have, how many significant figures? We have 3 significant figures for all of these values. And I have a 7 over here, so then this will go to 0.0924. That is equal to my Kc value. Okay, so we have our Kc. Now we need to solve for Kp. Well, we've done a problem like that before in the past where our Kp is equal to our Kc times RT to the delta N. And all we really need to know is what's our delta N value? Well, that's the moles in the final part of the reaction minus the initial part. So we have 2 moles of 1 and 1, so that's 2 moles in the final, and also 2 moles in the initial. So my delta N would be 2 minus 2, which is equal to 0. Therefore, that means then delta N has a value of 0, so then our Kp is equal to Kc RT to the 0 power, and you need to know that any number raised to the 0 power is equal to 1. Therefore, our Kp is equal to our Kc. Alrighty, so our delta N was equal to 0 because we had the same amount of moles on the products and the reactants. So this is a special case where your Kp is equal to your Kc. Alright, so recap. When you're giving initial conditions and equilibrium conditions, you need to construct an ice table. And just as a recap again, the last row in the ice table represents the equilibrium concentrations, and those are the values that you plug in to your Kc. And once you have Kc, you can solve for Kp by just knowing the delta N. Alrighty? Cool. Hopefully that's pretty straightforward by now. I think you guys might be getting the hang of it. I will see you guys in the next one. Thank you.